minutes. But ladies and gentlemen, I would like to start, but where I want to start is not with this Pythagoras problem that you see in front of you. I would like to start with what I like to call principles of trigonometry. And that is basically from grade 11. So I want to go over those principles, and then I will, after that, we will go to these problems. So I just want to go through my pages and see where I can write so I don't mess up this whole thing. Oh, this page is here so many times. Okay. Let's not worry too much. There is a clean page. So let me start. The first thing that I would like to discuss with you is what you all know, and that is cast. So that's one of the first things we do in trigonometry. You all know it. Why I want to talk about it is not because it's difficult. It's an easy way to remember where the functions are positive. The thing is, I always like to show the learners why are they positive there. And I do it for two reasons, if I can show you. First of all, I draw a basic sine graph, just the one from 0 to 180. So that is 180, that is our 360, that is 90, that is 270 and 0, and it goes up to 1 and minus 1. Now what I'm going to do is I'm going to draw vertical lines. These lines doesn't have any meaning. It's just a line. And I draw it at 90, at 180, at 270, and at 360. So as you now can see, here we have our quadrants now, the 4 quadrants next to one another. Now, when you discuss functions, trig function or algebraic functions, the learners must know where a function is positive and where a function is negative. And clearly you can see on this graph where is sine positive. Sine is positive in the first and the second, negative in 3 and 4. And I find this a very effective way of explaining to learners. But of course, they must know the basic graphs, but that they already do in grade 10. So we can bring this in and at the same time tell them if they ask where a function is positive, if it is above the x-axis or below. I'm not going to draw now the cos graph. You can do the same. You can do the cos graph. You can do the tan graph. Maybe there's just one thing I can quickly show you. If I draw the cos graph and I draw the vertical lines, you can see that is positive, negative, negative. So that is my cos graph. So if you look at tan, you can see tan is sine over cos. And in the first quadrant, sine is positive, cos is positive. So that means tan is positive. Second quadrant, sine positive, cos negative, tan negative. So with those two, we can also get the signs for tan. But in any case, they have the acronym cast, which they can remember. It's an easy way to remember where the functions are positive and where they are negative. You all agree, hopefully, with me that this is quite important. So the next thing that I would like to discuss with you, and that is reduction formulae. And that is 180 minus, 180 plus, and 360 minus. Now, what is the purpose of this? And the reason for these are that we want to change angles. We want to reduce angles to acute angles. So angles in the second, third, and fourth quadrants, we want to reduce. Now, I don't know if it happened to you. Many learners ask me, but why? Why can't we just use a calculator? And that is a question that I've got many, many times. People ask me, why can't I just use a calculator if the angle is not acute angle? The reason for that is that we would like them to be able to do the principles of trigonometry and not just calculator skills. Because with calculator skills, they think they can solve anything on a calculator, but they still don't understand what it is about. And that is why it's crucial that we have this, and we have special angles that goes with it so that we work with acute angles and we stay away from calculators. That is the main reason for this. And as you all know, whenever we use the reduction formulae, we use it together with a cast diagram. And that is quite important. So what I like to do is to show the learners, I start with sine 30. You can see where I'm going with it. And then it's the sine of 210. And then the sine of 330. So I took 30 degrees and I took sine. You can use cos as well. Now, the sine of 30, as you all know, is a half. The sine of 150 is in the second quadrant. So that is also a half because that is sine 30. Sine 210 is negative sine 30. So that is minus a half. And so is the sine of 330. And that is minus a half. So those four angles gives us the same answers. Two of them positive, where? First and second. Two of them negative, 3 and 4. Just that they can see that that is why it is important that we use the cast together with this one, with reduction formulae. The next thing I would like to talk about is 90 minus and 90 plus. These are the co-functions. Now, ladies and gentlemen, I am aware that there are many teachers who are doing the 270 minus and 270 plus as well. I personally don't think it's a problem. It is not in the syllabus, so it will not be directly tested. If you want to expose your learners and you have time and they can cope with it, of course, it's your choice. I'm going to stick on 90 minus and 90 plus. So with 90 minus 90 plus, this is on sine and cos, because the co-function of tan is cot, which is not in our syllabus. So we only apply co-functions on sine and cos. So when we look at 90 minus and 90 plus, my question to the learners I always ask the same question. I said, you remember when we use these, sine changed to cos? And they always say, yes, they remember that. I say, do you know why sine changed to cos? And they say, no. So I would like to show you what I show learners, why the name change. And I'm going to draw the sine graph. There's the basic sine graph. 90, 180, 270, 360, up to 1 and down minus 1, negative 90. So that is y equal to sine x or sine theta. Now what I would like to do is I want to look now at the sine of 90 plus theta. But as you can see, I look at it as a graph. Now, what we do with the learners, as from grade 10 and we're in grade 11 on functions, you notice that this is a horizontal shift. It's theta plus 90. And you hopefully remember when we do shifts, horizontal shifts, it works with the opposite sign. So that means we put this theta plus 90 equal to 0. So theta is negative 90. So it means it moves 90 to the left. So this at 0 will go here. This turning point will go here. The intercept will go there. The turning point will be here. And that intercept will be there. And I will try to join them nicely. And you will notice that this gives us the cos graph. And that is the very simple reason why y equal to sine of 90 plus theta is the cos of theta. And that is something that is extremely important. We use this reduction formula a lot. For example, you remember the questions. I always like this, this easy question, sine of 80 over the cos of 10. Simplify without the calculator. and you agree that is cofunctions. How must your learners recognize it? The key, 80 plus 10 is 90. If two angles add up to 90, cofunctions. Then you can change the 80 to 10 or the 10 to 80. So you all agree that this will become the cos of 10 because it's 90 minus 80 over the cos of 10, which will give you 1. So that is where we use this. There's something else that I would quickly like to show you. No, I can do that a little bit later. So I want to move on. We spoke now about reduction formulae, these cofunctions. So what I quickly would like to do is to talk to you about special angles. There are different ways to remember special angles. I personally don't really mind. When I was at school, we did the 3 triangles. So I hear many people still use it. I started to use the Cartesian plane, and I find learners find it easier to remember. So you only need to draw the first quadrant, and your radius is 2. So we draw not a unit circle, it's a radius of 2. There are your 3 angles, 30, 45, and 60. You start at 90, 0, 1, 2, 3, 4. You put the commas, and you go back 0, 1, 2, 3. I write very terrible here. And this one, because this was 0 and it becomes 4. We put them in brackets, and now you find the square root of all of them. Square root of 4 is 2, square root 1 is 1, square root 3, square root 2, square root 2, square root 3, and square root 4 is 2. And that's all they need to remember. So this is the 30, the 45, and the 60. So we start at 90, 0 to 4. We go back on the outside, 0 to 4, square root all of them. So if we want the cos of 30 degrees, we know cos is x over r. So you go to 30, cos of 30, x is root 3, r is 2, root 3 over 2. So I find it that this really helps the learners to remember the special angles. Of course, you know that majority of our learners, they must get the special angles, but then they still use a calculator. But in any case, there's nothing we can do about that. So ladies and gentlemen, the next thing I would like to talk about, and still these principles, you can see it's everything we do in grade 11, from the cast diagram to reduction formulae, special angles, and now let's look at negative angles. So if we look at negative angles and we have the sine of, let's say, minus x, cos of minus x, and the tan of minus x, then I think you all know that sine becomes and tan becomes negative, but cos becomes positive. The cos of minus x is positive, cos of x. Reason for that again is because our negative angle is in the 4th quadrant, that acute angle of x. And so that is my negative x now. And as you can see, it's in the 4th, and that is where cos is positive. What I like to do with negative angles, the learners must know these 3 rules. And the reason why they must know them is when they are dealing with problems that is in variables, then they must apply that. If they give them a sine of minus x, they must know. If it's an angle, so if they give them the sine of negative 150, for in case, part of a question, how will we? So we can use the rule, and the rule says it becomes a negative sine of 150, and then we use reduction formulae. So it's negative the sine of 180 minus 30, and that is 30 because 150 is in the 2nd. So that's negative sine 30, which is then negative a half. What I like to do instead is, if we look at the angle of negative 150, I hope you all agree that that angle is in the third quadrant, because this is direction is minus 150. So we go to the in a clockwise rotation. Now, what I like to do is to find that angle, because for every negative angle, there is a positive one. So I tell learners, you have a given negative angle, you don't work with it, you change it to a positive angle. Unless that angle is acute, then we rather use the rules, then it's much quicker. But for this one, I will say that the sine of negative 150 degrees is equal to the sine of negative 150 plus 360. So what I do is, whenever I have a negative angle, I add a rotation to it. And you all agree that is 100% correct in mathematics, that we can add a rotation to an angle, we can subtract a rotation to an angle, and the angle stays the same, the value of the angle. So as you now can see, we have 360 minus 150, which is 210, which is in the third quadrant. Sine in the third is negative, it's 180 plus, and that gives you negative sine 30, which is negative half, and you will see it's the same. So they may convert that negative angle to a positive angle. So it's all up to you what you think will work best for your learners. I like this. This is more the way I like to go. Normally, like I said, only if I give you the sine of minus 10 degrees, negative 10, then I say it's negative sine 10. Because they mustn't in any case know those. But if the angle is not an acute angle, then of course, I think it's much easier to do it this way. Then on top of that, I want to go back to the reduction formula. You are aware that almost in every grade 11 paper and grade 12 paper, your learners will get a sine of 180 minus theta, and not the sine of, that is what we normally get, sorry, my mistake. But now what they like to do is to say theta minus 180. So they flip the bracket around. Now, you hopefully, the 180 plus, you all agree doesn't matter. It's only the 180 minus that, and of course the 360 minus as well. Now, when I look at a theta minus 180, my idea is that this angle, that 180 is negative, and I don't like it. So what I will do is I will add 360 to it, which will now give me the sine of 360 minus 180, which is positive 180, and the theta is positive. And there I have sine of 180 plus theta. So the sine of 180 minus theta is the same as the sine of 180 plus theta, which is third quadrant, so which gives you negative sine theta. And I prefer to show learners this. If they change these two around, you are aware that we can also do a sign change and then to change it like this. So a negative outside that, and we take out the negative from theta minus 180. And now you can see that is a sine of a negative angle, and that gives you a negative sine of 180 minus theta, which is negative sine theta. So that is also an option. That is the algebraic route. And then, of course, if you use negative angles. By the way, the 361 is really pretty beautiful, because if I want to know in which quadrant this is, and I add 360, then I know immediately it's sine theta. So it's in the first quadrant. Which is quite straightforward. So, ladies and gentlemen, the main thing about all these, let's call it funny reduction formulae, we don't always know where they are on the Cartesian plane. And if we don't know where they are on the Cartesian plane, we can't say if they're positive or negative. That is why we need to know in which quadrant it is. Now, I don't know if, I hope you don't mind if I can just quickly show you something else. So if I quickly go back to the sine of theta minus 180, I showed you this now with negative angles. I also showed you to do this with algebra, the sign change, or you can do it graphically. Because we want to know the sine of this angle, in which quadrant is this theta minus 180. So let me draw a Cartesian plane. You all know the angle theta is in the first quadrant. That is my angle theta. If I take that angle and I subtract 180 from it, then I hope you agree with me, I will get here. So this is minus 180 from theta, which takes me to the third quadrant. So that means it will be negative sine theta. The learners don't always quite so happy with these drawings, but for you as teachers, I think it's good for all of us to know. If someone asks you, you can show them. All right. So ladies and gentlemen, I'm still trying to go as fast as possible here, but please, I'm not trying to rush. I'm just don't want you that we're not finishing too late. So, ladies and gentlemen, the next thing that I think I still need to talk about with you are the identities. And the identities, the one I mentioned, that is quite a one that everyone knows, that tan is sine over cos. And then, of course, the sine squared x plus cos squared x, which is equal to 1. And please, whenever you discuss this with your grade 11s and when you revise it with your grade 12s, show them the alternatives as well, because that is quite important in trigonometry in grade 11 and 12. So those are the identities for grade 11. So that takes me to the end of grade 11. So now all that we have left is one topic in grade 12. So ladies and gentlemen, majority of trig is in grade 11. I'm honest with you, you can't start your grade 12 trig if you didn't revise grade 11. I always revise all these principles before I start a trig grade 12 workshop. And what I'm going to do now is, I'm now going to go over grade 12, because grade 12 have only identities. So all of these are part of grade 12, and now we expand these identities. And that is two compound angles. The sine of a plus b. Now, ladies and gentlemen, sine a cos of b plus cos a sine b. Now, in terms of these problems with compound angles, when I discuss them with, yes.
Yeah, sorry, can I interrupt quickly?
Yes.
There was a question. Please explain the K360 for tan. I am just reading the question.
Okay. I don't mind. I want to believe the person who asked this question have a look in our textbook, and they notice there that I use 360 for tan. That is when we are dealing with equations. So I am just going to discuss equations with you. If you don't mind, if we can hang on with that. If I forget, will you just please remind me again, and then I tell you about it. The tan and the 360. I hope that is that what the person wanted to know?
Yes.
Okay. We will get to that. Yeah.
Thank you.
All right. So, ladies and gentlemen, I give them sine a plus b. You can give them any one of the four, because we've got sine a plus b, cos a plus b, sine a minus b, cos a minus b. What I like to do, and this is a possible question in an exam, I don't see they ask it a lot. It's something I like. And that is, you give them sine A plus B. Now you ask them to use this sine A plus B and find the rule for sine A minus B. So they can't just write it down because these are on the formula sheet. You ask them to find the rule for sine A minus B. So what you need to do is, to do that, is we need to change this A minus B to addition because I want to use this one. So I'm going to say it is A plus a minus B. And as you can see, this is now a compound angle for sine with a plus. So I can now use that given one, and I will get the sine of A cos of minus B plus the cos of A times by the sine of minus B. And now you can see why I do this, because now they must know those rules for negative angles. So sine A stays, the cos of minus B becomes the cos of B, and then I get the sine of minus B, this one. You agree that becomes a negative sign, so this positive becomes a negative. Cos of A will stay, and then it becomes sine of B. And you all agree with me, that is the rule for sine A minus B. And it's a very nice exercise. I don't tell them that this is a theorem or something they must know. I treat it like a problem. So I show them one and I ask them to do one. And so maybe we can do another one. We still look at sine A plus B. What about the cos of A plus B? So I ask you to use sine A plus B to find a rule for cos A plus B. Now, the first problem is the plus we're happy with, but that is not our concern now. Our concern is this cos. I want to use sine, so I must change it. And you all know this is a cofunction. So it's sine 90 minus A plus B. And now if I rework that at the inside a little bit, then I get 90 minus A plus a B. So I group the 90 minus A together, minus a B. That is because that negative goes into the bracket. And now, ladies and gentlemen, we have a second thing to do. So I take the minus in, 90 minus A is my one angle. Now it is minus B, but I don't want a minus because I want to use plus. So I say plus a minus B. So you can see now in this one, I have compound angles as well as negative angles. So we expand it now to the sine of 90 minus A cos of minus B plus the cos of 90 minus A times by the sine of negative B. Now, ladies and gentlemen, I'm running out of space here. So if you just look at this, the sine of 90 minus is cos A. Cos of negative B is cos B. So this will change to cos A cos B. The cos of 90 minus will become the cos of 90 minus will become the sine of A, and the sine of minus B becomes negative sine B. So that means this plus changed to a minus. So that means we will end up with cos A cos B minus sine A sine B. And that is the rule, as you remember, for the cos of A plus B. Now there's only one left, and this is the cos of A minus B. And then you also use 90 minus, and it works pretty easy. This particular one, this one that we did now, this cost one, the last one, this is the one that is of the three of them, maybe one that they can struggle with. So be careful with that one. Now, ladies and gentlemen, about these compound angles, it's really important that your learners they always tell me that it's on the formula sheet, so it's not a problem. I said, no, you must be able to recognize them. And to recognize them, you don't memorize them, you remember a pattern. So if I can explain to you the pattern, sine, there are two of them. And the pattern is the same for both of sine. And the pattern is sine, cos, cosine. That is the pattern. So whenever you see sine compound angle, the pattern is sine, cos, cosine. And the sign, that is now plus and minus, stays the same. What about cos? There are two of them. The pattern is cos, cos, sine, sine. And the sign is different. If it's a plus, as you can see what we did here, the cos of a plus b on this one, it changed to a minus, where when you work with sine a plus b, it is a plus. So they only need to know two patterns, the sine pattern, sine, cos, cosine, and the cos pattern, cos, cos, sine, sine. With sine, a plus stays a plus, a minus stays a minus. With cos, a plus changes to a minus and a minus to a plus. Please encourage your learners. Do it in class, that they say it after you. And when you do this trick, you ask them, and they must tell you what the rule is. That they practice it in class, that they remember it. So, ladies and gentlemen, that is compound angles. So we've got...
Here?
Yes.
Sorry, another question. On the summary of special angles, I want to know the value of the radius, especially on 45 degree. Is the radius the same as in 30 and 60?
Yes. Yes. Okay. If I quickly do that drawing again, that was 30, 45, and 60. You'll remember I wrote down your R is 2 because we work in a circle. So your radius is 2 for 30, for 45, as well as for 60. So if I, for instance, ask you what is the sine of 45, then you will say it's y over r. And y for 45, if you go 0, 1, 2, 3, 4, 0, 1, 2, 3, and 4. For 45, it's square root 2 and square root 2. So y is square root 2 and r is 2. So I hope I answered that question. So yes, for this particular one that I use, you will see I use it because that, can you see that 0, 4? You must find the square root. So that is 2, and the value here is 2. That shows you the radius is 2. So for all those angles. Okay. I don't know if there's anything else. Otherwise, we can start with some problems.
No more questions here. You can move on.
Thank you. So, ladies and gentlemen, I'm now at the notes that I gave you and that Roselle sent to you. What I did in the notes, and maybe you looked at it already, I decided to discuss it in topics. The first one, you all know that this question is always in a paper, and it's a question that learners do pretty well in, and very important because they can get good marks on this one, and these are the Pythagoras questions. After that, we're going to look at reduction, and that is now negative angles, reduction formulae, and so on. And more of them, reduction, but now it's with angles. These reduction in variables, these reduction in angles, and then to write in terms of, I hope you love this as well. And another one of that. And then we have identities. Identities, I selected two identities on double angles. You will see there are double angles in them. And then one on compound angles and another one on compound angles. So these identities, your double angle ones are the favorites. They are always there, but they did ask some of these compound ones before. And then we're going to finish the afternoon on equations. And then I will tell you about that 360. So, ladies and gentlemen, I'm going to start this question. You will notice in grade 11, they will only give you one of them. So if I show you here, that is one of them. Sine alpha is equal to -3/5, where alpha is between 90 and 270. That was for alpha. Do you notice now there's a beta as well? So this problem have two triangles. Sometimes they only give one, but the reason why this one's got two is if you look at the question, it is a compound angle, alpha and a beta, and that is why we need two triangles for it. So let's start with sine alpha equal to -3/5. I always suggest the learners must draw a tiny Cartesian plane just to determine their quadrant. Sine is -3 and 4. The restriction of alpha is between 90 and 270. It's this one. And that's 90 and 270. So as you can see, our triangle will be in the third quadrant. Now, sine is y/r. R is always positive. So that means the y will get the -3. You hopefully all agree with me that x will also be negative. If you look, it's on the negative side of the x-axis. And the 5, 3, that is the golden triangle of 3, 4, 5. So I'm not going to write down the Pythagoras here because it's a very easy one. So we will just say that x squared is equal to r squared minus y squared, which is 25 minus 9, 16. Square root is 4. So now we have x, y, and r for alpha. Now we do the same for beta. And that is 5/13, which is x/r. I draw a Cartesian plane. No, this is not cos. It's be cos 5/13, which is x/r. Cos is positive 1 and 4. The restriction is 273/60, which is the fourth. So that means this triangle is in the fourth quadrant. My x is 5. Our r is 13. And then y will be negative. So we say squared is 13 squared minus 5 squared. 169 minus 25, 144. So y then -12. And there we have all the information needed. So what we now need to do is just to answer the question. They ask us for the cos of alpha minus beta. So they must expand it. That is the cos of alpha, cos of beta, plus, you remember what I said? Cos is cos, sine, sine, a minus, that will be plus. Before for cos, the signs are different. With sine, the signs are the same. So this is sine alpha, sine beta. Yeah, that's correct. And now,
yeah.
Yes.
Sorry, there was just someone that had a question, or not question, just question mark, x equal -4.
Oh, yes, I see. I think I said it, but I didn't write it. Thank you very much.
Okay.
I didn't see it. There you go. All right. So now we're going to start substituting. Cos alpha, so we must go to the alpha triangle. And cos is x/r, and x is -4, and r is 5. So I say -4/5. Ladies and gentlemen, I always suggest to the learners to do this in brackets because some will be negative and they're going to make mistakes. Cos of beta, I go to the beta triangle, to this one now. And we have cos of beta, which is x/r, and x is 5, and r is 13. And then there's a plus, and then it's sine alpha. And sine alpha is -3/5. And sine beta is y/r, which is -12/13. I'm think I'm correct with that. And now it's just to simplify. You will notice these 5s will cancel. No, let's not cancel them. Let's leave them. I think that's going to help us a little bit. Otherwise, we can cancel them as well. But 5 times 13 gives you 65. And 5 times minus 4 is minus 20. And then you can see here, I can't cancel. And you can notice now why I wanted the 65 for this side. Negative negative is a positive, and that is 36. And now we've got a common denominator. So we can say 36 minus 20, 16 over 65. So that is to simplify, not really a problem. I don't think these questions, my experience is learners find them pretty okay, but please don't neglect them because this is where they can get full marks. It's really good marks and it's in every exam. Ladies and gentlemen, I'm going to this reduction. We spoke about reduction formulae. I hope there's one that's a wrong way around. I was trying to get one, but maybe not. But in any case, let's see. The first one looks pretty easy. Looks very much like a grade 11 question to me. But grade 11 is, of course, is also in grade 12. So let's do it. The sign of 90 plus. And sign of 90 plus is second quadrant. Yes.
Sorry, just another question. Someone asks how to allocate marks.
Yeah. Is it now for this one? I'm not sure.
Well, the question came through just now, so I assume so.
Yeah, it must be for this one. I must now think. They normally around about 5 marks. This one I think will be a little bit more, maybe closer to 6. I don't want to give it 7. I don't know. If you have a suggestion, put it up. That result, tell me. But I think we must maybe look at around about maybe 6 marks or so.
Yes, the person said it's for question 1.
Okay. So I will, first of all, I think I would like to give a mark for the quadrant. That's what I think. And maybe for the missing one, in this case, it was X. And we can do the same on this one, do for Y and for the quadrant. And then, sure. Now there's still a lot of substitution, but now what will we do here? I'm not sure. I'm really not sure. Maybe it's going to be a little bit more. I don't know.
Okay, someone else mentioned roughly 6 marks. Some of the knowledge they are expected to know from grade 11. And someone else said I would only allocate 1 mark per diagram.
That's what I agree with that person. That's exactly what I was thinking now when I looked at the rest of the problem. So I will give 1 mark for each diagram. I think that is a pretty good idea. And then maybe we can give a mark for, I'm not sure, must we maybe give a mark for this part, we're on 4, and then maybe towards the end, another 2 marks. I think something like that.
Okay,
I'm not sure.
It looks like, yeah, that's what the others also said. It's roughly 6 marks.
I think so, because if it's one drawing, it's normally 4 to 5 marks, depending on the question.
Yes, Mark or David Taylor said 1 mark per term and 2 for final answer.
Oh, you say 2 for final answer. Okay,
yes.
So 1 less there and 2 for this one. Okay.
Yeah, sure.
100%. Okay. Thank you. So let's quickly do this one. Ladies and gentlemen, I just need to get my color again, sorry. Sine of 90 plus, second quadrant, sine is positive, and it becomes the cos of x. Now again, I like to, because there's multiplication, I like to use brackets now. Cos of minus x is the cos of x. Remember, we said they must know those. And then plus the sine of 180 plus, third sine is negative. And then cos of 90 plus. Ladies and gentlemen, that is the reason why I selected this question to discuss with you today, was because of this. Cos of 90 plus is in the second quadrant. And cos in the second quadrant is negative. It is a very common mistake. Cos of 90 plus, learners write it as sine x. They say sine is positive in the second. So they look at the answer to determine the sine. And it's not, it's the given one. Cos was given to us. Cos 90 plus second, cos in the second negative. So therefore negative sine x. So make sure it is something that they really get wrong. And when I set questions, I always put it in. So let's just multiply, and I get cos squared x, and I think you can see what will happen here. That negative and negative is a positive, and the answer becomes 1. So a pretty straightforward one, but that was the catch, that they must be very careful. The next one is quite an interesting sum. So if I can start this one, this cos 90 plus, you will see it's the same thing which we just spoke about. And that, of course, becomes a negative sign. The sine of 180 plus is third quadrant. It's also negative sign. There's a minus. You see, and I already noticed this negative sign, negative sign gives me sine squared. So maybe a cos squared will also come. And then I say the sine of 90 plus, and that becomes cos x because sine is positive in the second. And then we've got the cos of 180 minus second quadrant, cos is negative, negative cos x. And then we have minus with that fraction. And you hopefully all agree with me, ladies and gentlemen, the moment that I have a negative angle, but there's a square, then the answer is always positive. If it's sine, cos, or tan, because the square will make it positive. So that sine squared of minus x will become minus sine x all squared, which will change it to sine squared x. So I just say to the learners, the moment there's a negative angle, but there's a square with a function, answer is positive. Sine of 150, second quadrant, 180 minus, that is the sine of 30 degrees. Now, as you can see now, we've got negative sign is sine squared. And I've got a minus, and a minus is plus cos squared. And you agree this whole part will become 1 in the next step. Minus sine squared x. We will leave it like that, divided by sine 30 is a half, the special angle. This becomes 1 minus, if I tip and times the half, I will get 2 sine squared x. And that is my double angle for cos. And that is the cos of 2x. I just remember I didn't discuss the two double angles with you. We must do it. We must do it. If everyone is happy, maybe before I continue with this, let me just get quickly a page, and that I just have a look and just quickly talk about the two double angles. So this, what I like to do as well, like I showed you with the compound angles, that they must find it. Then what I ask them to do is to do sine of a plus a for me. So I don't tell them it's a double angle. Double angles are also compound angles. The only difference is the two angles are the same. So this is sine, cos, sine. Sine a, cos a, plus cos a, and that is sine a. And you notice these two terms are the same, so that gives me 2 sine A cos of A, and that is the sine of 2A. So I like to discuss it with them and to show them from compound angles that we can find it. The cos of A plus A, if I can quickly go there, and that is cos cos, and minus because there's a plus, and that is sine sine, and that gives you cos squared A minus sine squared A. And you agree it almost looks like the square identity, and that is the cos of 2A, cos squared minus sine squared. But you agree we can also write it in terms of cos only. So then we say cos squared A minus, and sine squared is 1 minus cos squared. And you agree that will give us 2 cos squared A minus 1. And that is the cos of 2A. I can do it again, cos of 2A. I want to write it in terms of sine. So cos squared is 1 minus sine squared A minus sine squared A, which will give you 1 minus 2 sine squared A. So there they are. So ladies and gentlemen, I like them, and I even asked them these questions to find this rule for me for cos A plus A. And they get this cos squared minus sine squared. Then you ask them, right, use your identity, your square identity from grade 11, and write it in terms of sine and write it in terms of cos. It's important because when we discuss identities now, we really need this. So I'm going to go back, ladies and gentlemen. I just missed out on that. It's a little bit of a rush now, but let's continue and see. Equations, we are now at writing, yeah. So we are now at these questions, and that is reduction in terms of degrees, values. Now, ladies and gentlemen, one thing, if you see a question like this one, what I like to do always is, the first thing I tell the learners, have a look, and you see there's a plus and there's a product and a product. It almost looks like a compound angle. Cos cos, sine cos. So there's a little bit of an issue. The cos cos we're comfortable with, but then it must be sine sine. But maybe that cos of 105, because it's a given angle, we can use cofunctions and change it to sine. But the main thing is we must, first of all, change all the angles to acute. That's always the safest way to approach these questions. And that is, but it almost looks like there's a chance it can be a compound angle. But let's have a look. So if I look at the first one, the cos of 195, you agree that is in what? In the third quadrant, 180 plus 15. So 180 plus 15, yes. And cos in the third, of course, is negative. So that will give me minus cos of 15. Now I have the cos of 165. 165 is 180 minus 15. But cos is negative in the second. So it's negative cos 15. So as you now can see, these angles are now start to become all 15. And you will notice that on the other side now, there is a sign of minus 15, which will now give us negative sine of 15. So now it starts to look like this is not a compound angle anymore, but maybe this is going to become a square identity. The only thing now is we must now change cos of 105 to 15 degrees. So I'm not going to use 180 minus 105 because then you get 75. So one can do it, but then the 75 you must then convert to 15 again. So we can use 90 plus, and cos in the second quadrant is negative, and the cos will change to sine, and that is negative sine 15. And if I multiply these two terms, I get cos squared 15, and then I get plus sine squared 15, and the answer is 1. So a nice little question. It almost looked like it's maybe a compound angle, but finally it was not. Let's look at number 4. What will happen there if this is maybe a compound angle? If you look at this one, you will see sine, cos, cosine. And that looks pretty much like a compound angle, but we can't say yet. The only thing that we are happy with, it looks like these, you see, those are the same. So we sit with this one and we sit with that one. So that -6 is already acute. So let's change this 114. Sine 114 is 180 minus. Sine is positive, and 180 minus, I think I'm correct with 66, times by the cos of minus 6 degrees is the cos of 6 degrees. So we just write it as a positive angle. And then we say that minus, and then I'm going to do the cos of 246. Now the cos of 246, that is in the, where will that be? 270 in the third, and cos is negative in the third. So it's 180 plus, and that sounds to me like 66. The cos of 66, and you see we're quite happy with that, because here we have the 66 also. And now we multiply it with a sine of minus 6, which becomes negative sine 6, and we get minus the sine of 6 degrees. So let's just rewrite this quickly. It's the sine of 66 times by the cos of 6. There are 3 negatives here, so which will leave you with a negative. The cos of 66 times by the sine of 6. And I hope you can see the pattern. So now you understand why I feel very strong learners must know these pattern of compound angles. Do you notice it's sine, cos, cosine? That is a sine compound angle. And sine compound angle keep the same sign, this minus. So this will become the sine of 66 minus 6, which is the sine of 60 degrees, which is √3/2 if you use your special angles. And that is quite a nice one. If you look at what was tested in this question, quite a lot was tested here. There was reduction formulae, of course, cast, negative angles tested here, compound angle, and then special angle. So it's a lot of trigonometry in one question. But please tell your learners they must never be afraid of these questions. Particularly like this one, they're always very worried about this 2.2 because it looks such a big question. The nice thing about it is they get marks for every step they are doing. So I tell them, just start, just do them, and you will get marks. And you can finally do pretty well. Ladies and gentlemen, sine of 10 is P. I don't know if you also like these questions as much as I do. I pretty much love them, to be very honest with you. I think they are absolutely great. And the reason is they can't use a calculator even if they try, because we write in terms of P. So 2 things important. The same, and we want to get the angle the same. So you notice that given to us, I'm just going to write it down that it just stand out here, that sine 10 is P. They ask us sine 190. Now 190 is in the third quadrant, so it is sine, so I'm not worried about the sine. I want sine, but I don't want the 190. I want to use reduction formula. So 190 is in the third, sine in the third is negative, and that becomes the sine of 180 plus 10 degrees. And there I've got sine 10, and my answer minus P. Easy as that. What about cos of 10? You can see what is this? What this one is? Co-functions. So the first one, reduction formulae. The second one, co-functions. Now, when I do co-functions here, cos of 80, first quadrant, cos is positive, cos changed to sine, and it's 90 minus, it's sine 10, and the answer is B. So, ladies and gentlemen, what about the cos of 10? I want you to carefully look at this one. Cos of 10, given to us sine 10. So the angles are fine, but sine and cos. Now, to change cos to sine, we normally use compound angles. But you hopefully agree with me, if I'm going to use a compound angle here to change cos to sine, then the 10 will change to 80. So then I have sine, but I don't have the angle. So either way, we are a little bit stuck here. So, ladies and gentlemen, I want to show you a way. I'm pretty sure I know how you will do this one. And I've got no problem with that. We can talk about it just now. I just want to show you how I like to do this question. And this only for these, where if sine 10 is given, they ask cos 10, or cos 12 is given and they ask sine 12. Angles the same, cos and sine. And I quickly want to show you something. Cos squared x is 1 minus sine squared x. That's our square identity. What is the condition for this identity? That the angles must be the same. So we can change sine to cos and cos to sine by using compound angles. No, sorry, not compound angles. No, I can't get the name, but you know. To use 90 minus 90 plus. But if we use the square identity, we can also change sine to cos and cos to sine. Can you see this one? Cos changed to sine. So let me show you. It's cos squared 10 is 1 minus sine squared 10. So what is the cos of 10? It's the square root, which is 1 minus b squared. Now, I just showed you all the steps so that you can see exactly what I did there, but I quite like to use the square identity because it is another tool to change cos to sine and sine to cos. But the condition, the angles must be the same. That is the important one.
Yeah.
Yes.
There is a question. Can you use a diagram?
Yes.
To get this answer.
I was waiting for the question. You remember I said to you, I am pretty sure I know how you will do it. Majority of teachers are using a diagram. I've got absolutely no problem if you would like to use a diagram for this one. It's the same way we did it before. I don't know. Maybe you can say if you like me to do it with a diagram, or are you all right with it? I just want to make sure. Shop. So 10 degrees.
The person says she's fine with it.
Yeah, they surely you can use a diagram. Normally, when I discuss this with the grade 12s in particular, I show them both the diagram because they must know Pythagoras. We spoke about it already. Always remember the 10 degrees is in the first quadrant. So they can use Pythagoras for it, and you will get the same answer or just the square identity. The sine of 20, remember 10 was given. It's very obvious that this is a double angle, 2 times 10. And now we write it as 2 sine 10 cos of 10. Now the sine of 10 is p, and the cos of 10 is the square root of 1 minus p squared. So you will see this one is now easier because of the fact that I asked this one already. But in an exam, they may ask only this. They may ask only this one and not the one before. and you are then with me, they must now find the cos of 10, either using this or a diagram. But then the question will be most probably way more marks than what I did now. But if you have cos 10 already, this question then much easier. But just keep that in mind. All right. Of these problems, this one is the one the learners struggle the most with. Now, I want to tell you, before I give you the answer, just tell you how to explain to your learners how to look for it. You know, if we tell our learners, this is what you do, then they will not be able to figure it out. So I want you to, when I have 55, it's a cos. I can use a co-function to change it to sine, but you agree 90 minus 55, I can't do anything with that angle. So co-function is not going to help me. It's not a double angle. It's already acute. There's only one thing left, and that is compound angles. Now, the key with compound angles in these problems, you must use 10 degrees. So 10 degrees you need to use. And then you have a choice of 3 special angles. Which special angle with 10 will give you 55? And I don't think I need to tell you. You all know. And you all agree this is 45 plus 10.
Yeah,
now,
just another question.
Yes.
Can I quickly
Yeah.
read to you? Okay. Someone asked, can you show us how to get cos 5 from this diagram? And then someone else asked, am I correct when I say it's because cos in brackets 10 is in the first quadrant when a learner asks why we take only positive for
Yes.
a square root?
100%. Ladies and gentlemen, I didn't say it. I'm glad someone now asked the question. On this part, let me just get my... on this one, you will notice I didn't put a sign there. And the square gives me a plus and a minus. I didn't use the minus because it is the cos of 10. And 10 is in the first quadrant, so this answer must be positive, and that is why it's a positive one. Another question, that cos of 5, you want me to sweat here today. The cos of 5, ladies and gentlemen, is one of those very awkward questions. Because in our old syllabus, and if you have a few miles on like myself, when I did matric, it was all the trig functions, all 6 of them, and I think some of you maybe as well. Now, part of that syllabus, we also did compound and double angles, but we also did half angles. And if you now say sine of 10 is p, find the cos of 5, you now move to half angles. It is possible to do it, but it's not so straightforward. It's quite a high-level question. So I would like to ask, I don't mind showing you, but I must get through this stuff first. So maybe if we have time at the end, please, can we then talk about it? I don't want to brush you off. That's not the case. Those questions are awkward, but I've seen it once appear, and I asked the exam panel for some of them, and I said, these half angles, are you sure? They said, yes, they must just use double angles in reverse. Okay, so that is basically the hint that I give you. You use double angles in reverse to get to half angles. But in any case, you know what is going to happen here. We are going to now expand this as the cos of 45. This is cos of 10 minus sine 45 sine of 10. If it's okay with you, special angles, that's root 2 over 2 for both of them. And cos of 10, we did it already. It's 1 minus the square root of p squared. and the sine of 10 is b. If you don't mind, then I just leave it there. So we just, again, we have the cos of 10 already. Sine 10 was given, so therefore we didn't need to find cos 10 again. These are the most popular ones. But I decided to give you one that's a little bit more interesting. If tan 192 is equal to t, find the sine of 24. I decided to give this, to do this question with you for the reason it's a little bit different, because this tan 192 is pretty awkward. And then we have the sine of 24 that we need to find. So where do we start? My suggestion is we start with tan 192, because we don't like this 192 angle. So we just want to reduce it. So I think you will all agree with me that this 192 is in the third. It's 180 plus 12, and tan in the third is positive. So it is the tan of 12 degrees. You agree? And that looks a little bit better. Now we have the tan of 12. Now, if you look at what they ask us for the sine of 24, I hope you noticed this was 12 degrees. So it definitely looks like this is a double angle. And it's a sine double angle, so it gives you 2 sine 12 times by the cos of 12. But what must we do now? We want to write this, the angles are good, but given to us is tan, we want sine and cos. And ladies and gentlemen, now we don't have a choice. That question, one of the colleagues asked earlier, if you can use a drawing, yeah, you must use it. The square identity is not going to help us now. So my 12 degrees, first quadrant, you put t over 1. Tan is y over x, so y is t and x is 1. So that means if we find our radius here, for this one, we say r squared is equal to x squared plus y squared. It's equal to 1 squared plus t squared, which is equal to 1 plus t squared. So that means r is equal to, again, positive, 1 plus t squared, because r is always positive. And now it's a matter of substitution. So now you have x, y, and r, and now we substitute those two. Sine of 12, y over r, and it's t over the square root. And cos of 12 is x over r, and it's 1 over that square root, 1 plus t squared. You see, 2 times t gives you the 2t. Square root times that square root gives you 1 plus t squared. And as you can see, that is what the question asks us to get. So a little bit of a more interesting one in terms of, so I didn't just want to do sort of the normal ones. I thought I'd just show you something that's a little bit more exciting as well. Ladies and gentlemen, while I'm on the topic of these questions, I don't know if you all know, but majority of these questions are coming from our new grade 12 textbook. If you can see it here, you will notice it says here new edition. So if you're interested in the new textbook, please ask for the new edition. It's printed in yellow on this page, grade 12, and get yourself a good textbook. Ladies and gentlemen, it's now time for identities. So I've got 2 topics left, and I hope you will be able and allow me to go past 5 because of our late start. I don't know, would you like a 5-minute break, or can we just go on? I'm happy to go on, but unless people quickly want to stretch legs and we break only for 5 minutes. Any suggestion? We continue? Yeah, happy. Ladies and gentlemen, these identity problems, it's a real issue when we see a double angle for cos. Double angle for sine is not so much a problem. Double angle for cos is the issue. So I would like to show you how I like to focus on these identities in terms of double angle of cos. You know, double angle for sine, it's not a problem. Double angle for cos. Remember when I spoke to you earlier, there are three possibilities: that cos squared minus sine squared, and then 1 minus 2 sine squared, and 2 cos squared minus 1. Which one must we use? So let's start with this left-hand side. You will see the left-hand side looks impressive. And then we see if we can get it to tan x on the right-hand side. So what I like to do is I am not going to substitute cos 2x now. Maybe it sounds funny, but I prefer to leave it because I don't know enough yet. I first want to change everything else. Sine of 2x gives me 2 sine x cos x minus the cos x. And if I look at this denominator, I notice that there's a common factor of cos x, and it leaves me with 2 sine x minus 1. Now I want to stop right there for the time being. If you look at this denominator now, don't you think that will tell us what to do with that cos 2x? Must we write it in cos or must we write it in sine? That is now the main thing we need to check here. Now, let me show you how I think about these things. I say, this cos, I don't want to get rid of it, because remember, there's a tan, and the denominator is cos. So I want this cos. I don't want this 2 sine x minus 1. I must get rid of this. But I want the sine at the top. So I want the sine at the top to give me the tan, and I want this one at the top so they can cancel. I hope you agree with me. I'm going to substitute the sine one for the cos double angle because I want sine above the line. And that is how I reason it to make sure I substituted the one I need to substitute. Mathematically, anyone is okay, but it doesn't mean they're going to work out. So that is the danger. So I say 1 minus, and I say 1 minus 2 sine squared x. That is the double angle minus the sine x. And now we can continue. You agree with me, 1 minus 1 is 0. That negative is positive. So I will get 2 sine squared x minus sine x. And I think you can already see that there's a common factor of sine. That is what we were looking for. So I take out sine as the common factor. I'm left with 2 sine x minus 1 over cos x, 2 sine x minus 1. They cancel, and the answer is tan x, which is the right-hand side. I think it's pretty lovely. I hope it makes sense. Ladies and gentlemen, I always, when I explain it to the grade 12s as well, I say to them, don't rush with a cos double angle. You're going to substitute one that you think of, and it's maybe not the ideal one. Do the rest, simplify, and just get an idea. Also look at the right-hand side. What do you want to get? And that normally gives you a guidance on, it guides you a little bit how to get to that. There is another one, and you will see this left-hand side's got also 2 double angles, one for sine and one for cos. And that is now something to get. This one a little bit more exciting than the one we just did. And let's start with the left-hand side. If you're all happy with the previous one, I just want to remove some of it to create space for me, if it's all right with everyone. Okay, so let's start. I don't think I'm going to have enough space if I do it below, so let's start a little bit higher. I'm not going to write the question again. I'm going to start to change it. That sine of 2x, no problem. It's 2 sine x cos of x. And then I say minus 2 sine x. That one we don't need to do anything. It's just the 2 sine x. And my denominator is the cos of 2x minus 1. And now again we sit with this cos 2x. Which one is it? What do we want for that cos? Do we want the cos one? Do we want the sine one? Before we do, let's look at the numerator. And I notice in the numerator there's a common factor of 2 sine x. And that will leave me with cos x minus 1. Now the big question. What will we do next? This one, if you look at the right-hand side, you notice that we've got sine below the line. The tan below the line is a sine over cos, and if we flip it, it's cos over sine. So that's also a sine below the line. So I get a funny feeling that we must change it to sine. And that's my gut feel if I look at the right-hand side. And I must get rid of the sine above the line. So let's see what we get if I substitute this one with sine. So the cos of 2x is then 1 minus 2 sine squared x minus 1. 1 minus 1 is 0, so I get negative 2 sine squared x. And you hopefully now can see that maybe it's easiest to cancel the 2's in the meantime. And now I can take sine into the bracket. Maybe that's a pretty good idea. No, we don't need to. We can cancel the sine with this square. Sorry, I didn't even see that. I want to make it more exciting. So now we end up with cos x minus 1 over negative sine x. I don't want a negative here, so I'm going to take the negative to the top. And do you agree it's going to swap the two terms if I put the negative at the top? Now, when I look at this one, you notice I've got my sine below the line, which I want. And now I can write it as two fractions. So I can write it as 1 over sine x and then minus cos x over sine x. This 1 over sine, we're happy with it. And no, not equal. Cos over sine, of course, is the same as sine over 1 over minus, it's 1 over sine over cos, which is tan x. So we just reverse that division. And there we have the right-hand side. So we prove them equal. These problems are on double angles. They are very popular in exams in grade 12. You need to make sure that you explain it. It's not enough that you just tell the learners, this one substitute the sine one, this one the cos one. You must give them a sort of a feeling. I know it's difficult to explain, but give them a sort of a feeling on how to see, and not just to rush into the cos double angle, that they be patient and simplify the rest and see if they can't see it. All right, let's look at compound angles. Now, ladies and gentlemen, this is quite something if you start looking at these. I quite like them. My experience is the learners don't like them. They're pretty long, but they're not too difficult if you know how to look at them. I want you to look at all the angles given. There's a 3x, there's a 7x, and there's a 5x. If you look at the right-hand side, that is what we want. We want the 5x. I don't want 3x and 7x. I want 5x. That is what I have on the right-hand side. So what must I do with 3x and 7x? That will give me 5x. So I'm asking you for a compound angle. Which compound angle using 3x and 5x, or think of 5x, 3x, what must you do with it to get the 5x? So let me start with this left-hand side. That sine of 3x, I hope you agree with me, I can write as 5x minus 2x. Because that gives me 3x. And can you see I have the 5x? That's what I want. And the 2x is a double angle. So I use the double angle with 5 to get 3. And you maybe can tell me now what you will use for 7x. The same thing, just with plus. The reason why this works so well, and we always look for this, a plus and a minus, because we're going to, in the next step, we're going to expand it. And when we expand this, 2 terms will cancel and the other 2 terms will be the same. So let's just do the numerator, and we're going to do exactly the same thing. It is the cos of 5x minus 2x plus the cos of 5x plus 2x. But now, ladies and gentlemen, you must now bear with me. I must now try to expand top and bottom. Let me see what happens. It is sine 5x cos 2x minus cos 5x sine 2x plus sine 5x and then sine 2x. All right, there is the numerator. Now, before we do the denominator, always look for the negative term. Cos 5x sine x is negative. Cos 5x sine 2x is positive. This term, that term will cancel. And if you look at the 2 remaining, they are the same. So we get 2 of them. Let's just expand the denominator. That will be cos cos plus sine sine. And it is cos cos again. And that is 2x. If you look at this negative one, just look for the positive one that's the same, and it's this one and that one. If we now look at the numerator, I've got sine 5x cos 2x. I have it twice. 2 sine 5x cos of 2x. If I look at the denominator, I've got cos 5x cos 2x, cos 5x cos 2x. I have 2 of them. Cos 5x cos 2x. And your answer, tan 5x, which is the right-hand side. So you can see it is very easy to make mistakes because it's all this expansion that you need to do, but it's a critical, important principle that they must be able to do. I have a problem. I think it's our very last question where we're going to use this principle again, but then we do it with degrees. And this one is in terms of variables 3x and 7x and 5x. So if we look at this one is much easier. I was supposed to swap the 2 around. I only realized later. But this one, quite easy. I think all of you will be able to do it. The question is, which 2 angles are you going to use to get 3x and 5x? And I think it's quite obvious. Look at the right-hand side. We use 4x and x. So I'm going to say it's the sine of 4x minus x plus the sine of 4x plus x. Now we expand them. 4x cos of x minus cos 4x sine of x cos 4x sine of x, cos 4x sine of x, they will cancel. I end up with 2 sine 4x cos of x, and I pretty much think that is the right-hand side. So, ladies and gentlemen, I hope I assisted you a little bit with these identities. The thing is not only to have the solutions of these questions. What I try to do is to give you ideas on how to explain it to the learners, because they don't find identities very easy. But they must know them. They must know them very well. Ladies and gentlemen, our last topic for today, equations. And I prepared a few questions. First of all, I only noticed it. I prepared and I typed these all up. And then I started to do the questions to see and to check if there's mistakes, and I already sent it out. So will you be so kind to just scratch that square out for me? I'm really sorry that the square must not be there. It's 2 sine 2x equal to 3 cos of x. So what will we do? We will start with 2. The sine of 2x is 2 sine x cos x minus 3 cos x, I'm just going to bring it across, equal to 0. I think you're all happy that this will become 4 sine x cos x minus...
Sorry, can I interrupt quickly? There's
Anytime.
just a question, but it's been asked some time ago. My apologies, I missed that one. When he gets a gap, please, can he answer my question here below, which is, sorry. Okay. What is your opinion on using the calc for special angles? They can actually get away with it most of the time, in brackets, with the exception of tan 30, with a calculation gives the answer with a rationalized denominator. How strict should we be? No need to interrupt and answer immediately. Oh, okay.
But it's an easy one to answer. So let me quickly answer because I may be going to forget. It is a real problem. Special angles, they can do, most of them, they can get on a calculator and examiners will not be able to pick it up. So my take on it is, and I'm going to be absolutely frank with you how I see this. When we discussed this CAPS panel, the panel when we did it, I asked the same question. Does it still make sense that we say no calculator if we know the learners use it already in any case? And unfortunately, the answer is yes. And there's a simple reason why we want it. We want to avoid calculators in trigonometry as far as possible, because it's not about just calculate something. You notice as we do, all these principles are so important, and we want to lay that down, these principles. Now, and there's another reason. So I always say to teachers, it's for you to decide. Do you have children in your class that will go to university and maybe study mathematics as a subject? Calculators are not allowed in first year mathematics. I tell you, my students ask me to explain special angles for them because they couldn't do it. And now they can't use a calculator and they were stuck. So for the sake of students who go to varsity, I want to encourage you to show them how to do it without a calculator. That they must make sure they know how to do it. And that little diagram, very easy to remember. All right, can we continue? So this one, you will see I changed the double angle, and now there's a common factor. So I'm going to take out cos x as a common factor because this is an equation, huh? We don't prove. And I get 4 sine x minus 3 equal to 0. And you agree I'm now going to get two equations. So I get cos x is 0 or sine x is equal to 3/4. Now, ladies and gentlemen, when we look at cos x equal to 0, I would like to tell you how I like to do it with the learners. I don't want them to work out a reference angle on a calculator here, because 0, you don't know exactly what to do. I tell them the easiest way to do it is that they must quickly think of the cos graph, just the basic one. And where is this graph? 0. At 90 and 270, and there are your two solutions. So we will say for this one, we will say in the first one that x is equal to 90 plus k times 360, or x is equal to 270 plus k times 360, where k is an element of z. And that is the first half of the solutions. The second half is now sine x equal to 3/4. We now need the reference angle, because this is not a special angle, so they need to use a calculator. I've got it as 48,19. I think I'm correct. And now sine is positive, so we work first and second quadrant. So it means we will say that x is equal to, in the first quadrant, I just wanted to make sure that I've got this correct. No, my angle is wrong here. I thought I've got something wrong. This is not the reference angle. If you guys can maybe just double check for me, but I think my reference angle is 48,59. So my x is then 48,59 degrees plus k times 360, or it is then, it is sine, so it's second quadrant, so it's 180 minus 180 minus, so you will get x, so we must say or, x is equal to, and 180 minus will give us 131,41 plus k times 360, where k is an element of z.
Yeah, there's just a quick question. Will x equal 90 plus 180k be accepted as the only solution for the first part?
So I just want to make sure, I got it correct. What you said, she said if she wrote 90 plus k times 180.
90 plus 180k be accepted as the only solution for the first part.
You see, it will be yes if they give you the same solutions. If I just quickly think, I almost want to say yes. I get the feeling that you will get, because if k is -1, you get -90. Yeah, I think so. I think you can do it. I will be careful to change it to one solution. That is almost what I do with tan, but I do the opposite with tan. I take the one solution to two solutions, because I want to keep all these things the same. I don't think I will recommend it, not for the sake of the learners. I'm not so sure if they will be comfortable with it. But if it works for you, I think my suggestion will be, if you can take both of them and work out k -1, 0, and 1 for both, look at your solutions and see if you still get all the solutions if you use only that one solution. And that's the only way to compare it. We must write them down. All
Okay,
the
someone,
solutions for the two, and then the solutions of that one, of the
sorry,
180.
else mentioned, I would say definite yes. From 90 degrees, there is a solution every 180 degrees.
Yes, that's why I say I'm pretty sure it's correct. I agree. But just a way to double check is to expand them and substitute k to see if you get the same answers. All right, can we do the next one? This one was a sine double angle. The next one is a cos double angle. So I just want to remove some of this because I'm going to need the space here. So let's start. 3 cos 2 theta plus cos theta plus 1. We need to substitute cos 2 theta. I hope you agree with me in this particular case. It's not too difficult to know which one to use, because you can see we've got a cos already. So we're going to use the cos one for the double angle. So we're going to say 3 times the 2 cos squared theta minus 1 plus cos theta plus 1 equal to 0. And you can see it start to look like a trinomial. The first one was common factor, but you all know trinomial also very, very popular. So this will give us now 6 cos squared theta minus 3, but I'm first going to write down the cos theta. There's a 1, and the minus 3 plus the 1 is then minus 2 equal to 0. And now we need to factorize this beauty. Ladies and gentlemen, I'm sure some you do it as well. I just want to make sure. What I like to do on the side with the learners, I say, if you're not so sure of this one, write it in terms of k or x or whatever you want. 6k squared plus k minus 2. Just the normal trinomial, and we can factorize it easy. I think 3k and 2k will do the job. 2 and 1, that gives you 4. That gives you 3. The difference is 1. The 4 must be positive, and the 1 must get a negative. So we will get 3 cos theta, 2 cos theta, and then we have a plus 2 and a minus 1. And there are the two brackets. These are my two linear equations. So now I can split them, and I can say cos theta is equal to negative 2 over 3, or cos theta equal to a half. And now we need to find reference angles. So the cos theta a half is easy, reference angle 60. There's 2 over 3. We must go and find the reference angle of that one. So let's quickly do the cos one. First, this reference angle here, I think is the one I wrote earlier, the 48,19. Cos is negative. Cos is positive first and second. So cos is negative 2 and 3. So I would say theta is equal to 180 minus the reference angle, which will give you 131,81 plus k times 360. Or in the third, it will be 180 plus this 48. And that will give me 228,19 degrees plus k times 360. And always remember k an element of z. So this is the 1/2. Now we have the cos theta, which is equal to a half. I'm just going to squeeze it in here. The reference angle is 60. So you agree they are not too bad. Cos is positive first and fourth. So theta is equal to 60 plus k times 360, or theta is equal to, in the fourth 360, so it's 300. I think I'm correct. Yes, 300 plus k times 360, where k is an element of z. And there we solved it. Interesting one. So you can see double angle for sine on it, double angle for cos. There's a few more. So let's have a look at the next one. There's a sine squared and a cos. And I think you know, I have a sine squared, a term with a sine squared and a term with a cos. There's no double angle. That sine squared I'm going to take to cos. So I'm going to say 6, 1 minus cos squared theta minus 7 cos of theta minus 3 is 0. Let's remove the brackets. Ladies and gentlemen, I wrote terrible here. I just want to do it again. If we solve it, we will get minus 6 cos squared minus 7 cos theta. 6 times 1 is 6, and there's a minus 3. So that means plus 3 is equal to 0. Let's multiply with a negative. Then we get 6 cos squared theta plus 7 cos theta minus 3. Again, 6k squared plus 7k minus 3 if we want to factorize it quickly. And then we can write down those factors here. And then we solve them. I think you will agree with my factors. I think it's 3k and 2k. And I think that will be 3 and 1 because this is 9 and this is 2 and 9 minus 2 is 7. So that is correct. So it's 3 cos squared and 2, not cos squared, but cos. And then we have a 1 and a 3. And we want the 9 to be positive and that negative. So now we can write down the two equations. So we can say cos theta is a third, or cos theta is negative 3 over 2. Now, ladies and gentlemen, when you get a question, I'm sure you know already, but your learners maybe don't know it. Ask them to use their calculators and ask them to work out the reference angle for this one. I normally don't tell them unless they can tell me, and then I ask them do it, and they try, and they will get an error because negative 3 over 2 is outside the range of cos. Remember cos and sine? Between minus 1 and 1. So that basically means that this one have no solutions. Not applicable, or we can maybe rather say no solutions. So we only need to solve cos theta equal to a third. So our reference angle is what we need, 50,53. Our reference angle, that's 50,53. And now we're going to write the two solutions. Cos is positive. So it is first quadrant, theta equal to 50,53 plus k times 360, or in the fourth quadrant, theta is equal to 360 minus that 50. Am I correct with that? I'm not sure. I think I've made a mistake here somewhere. Did I? 50, it's 50. Cos is positive in the first. Yes. No, that is correct. And then in the fourth, that will be 360 minus that 50,53. Maybe you can just check, please, with me if I've got this answer correct in the fourth. I think I have it. I say it's in the first quadrant or in the This is cos, yeah, so it is the fourth quadrant. I'm sure this is correct. All right, I think that looks good. I notice if I saw correctly, someone just said there's maybe a mistake on my reference angle.
Yes, someone said, yeah, sorry.
Yeah, it's possible.
The reference angle is 70.53 degrees.
Yeah, let me.
The method is correct.
Yeah, no, I know that, but I could make, it's possible I could make a mistake on this reference angle. Cos of a third. Yes, you're correct. It's 70,53, not 50,53. Ladies and gentlemen, I apologize for that little mistake. And then, of course, everything else that will change to 70,53. And this one will change as well. And this one will be 360 minus 289. Okay, I think we've got the answer correct. 70,53. Thank you for picking that up. All right, ladies and gentlemen, that is it. Let's do the next one. The next two questions are similar questions. You will see this one is a cos equal to a cos. And then we have a sine equal to a cos. Now, if I have a cos equal to a cos, and the angles are different, then I may equate them. Because cos is positive in the first and fourth quadrants. So I'm going to start in the first quadrant, and I'm going to say in the first quadrant, 3x is equal to x plus 20 plus k times 360. And if I take the x across, I get 2x is that 20 degrees plus k times 360. And x is equal to 10 degrees plus k times 180. Or we go to the fourth quadrant. And then you go 3x is equal to 1. No. 360 minus that x plus 20. Please, it must be in a bracket. Plus k times 360. K an element of z. So we have 3x is equal to 360 minus x minus 20 plus k times 360. This minus x will give us a 4x. 360 minus 20 is 340. I think so. Plus k times 360. Just double check for me if I don't make mistakes here. 360 minus x minus 20 plus x, 360, yeah. And now we divide by 4. So x is equal, 4 goes in there, 8 times 32, 4 goes that, 85. Plus k times, and I think that will be 360 divided by 4. I think that will be 90 degrees. I think that's the two solutions. Looks correct to me. So we have already cos equal to cos. Angles are different. Then we can just solve it within the quadrants. If we have a sine, I didn't select one, they're pretty easy. If I have a sine equal to a cos and the angles are the same, then we divide by cos and we change it to tan. And a sine equal to a sine and a cos equal to a cos, we can solve straight away. And if we have a sine equal to a cos and the angles are not the same, we can't take it to tan. We now need to use cofunctions. We must get the names the same. So the question is, which one will you change? I will change the cos one because it's got only x with it. So I will say that this is the sine of 90 minus x. I subtract the angle from 90 and then cos change to sine. And now you can see we've got a sine equal to a sine. And sine is positive in the first and in the second. And now we do it similar to what we did the previous one. So in the first quadrant, we will say 3x is equal to 90 minus x plus k times 360, k an element of z. Bring it across and I will get 4x is 90 plus k times 360. We divide by 4, we get x is 45, 22,5, I think, plus k times, and that will be 90 degrees. Or we go to the second, and then we have 3x is equal to 180 minus 90 minus x plus k times 360, k element of z. So 3x equal to the 180 minus 90 plus x plus k times 360. That plus x, you take it across, we can change that to 2x. 180 minus 90 is 90 plus k times 360, and now we divide by 2. And that is 45 plus k times 180. So I wanted to discuss these different ones with you. A cos equal to a cos equal to a sine, and a sine equal to a cos, and sine equal to cos, angles not the same, angles the same, you take it to tan, angles different, cofunctions. And that is what your learners must remember. So ladies and gentlemen, I'm at the last question. Sine x is equal to sine 43 plus sine 17. I ask to solve for x, or I ask for general solutions. Just not to waste too much time here, that 43 and 17, you must find two angles. If you add them, they must give you 43. If you subtract them, they must give you 17. And one of the angles must be special. So you use 60 with an angle, 45 with an angle, or 30 with an angle. Which special angle, which angle, if you add, will give you 43. If you subtract, will give you 17. I would have loved to see your faces so that you can tell me. But I'm pretty sure some of you got it. What about 30 plus 13? And then 30 minus 13. I think you must agree with me, this is quite beautiful. Now it's similar to what we did way before. Remember when we did those identities, I told you we're going to get something like this, but in degrees now. Now we need to expand them. 2 will cancel, 2 will be the same. So I will get sine 30, cos 13, plus cos 30, and then sine 13 plus sine 30. This one and this one will cancel, and you end up with 2 sine 30 cos of 13. And that is sine x. So now we know that sine x is equal to 2 sine 30 is a half, and a half times 2 is 1. And then we have the cos of 13. So now I end up with sine x is the cos of 13. So you now can see why I did the previous questions with you. I've got a sine equal to a cos, and the names must be the same. So I will not change the x, I will change the 13, and I will write it as the sine of 77, because it is 90 minus, and then cos change to sine. And now we have the angle. It is positive, sine 77 is positive, first and second. So in the first quadrant, what will x be? 77 plus k times 360. Or in the second quadrant, x will be 180, 180 minus 77 plus k times 360. And there we have it. And what is this? 103. So I want you to remember this principle where we must use compound angles in terms of degrees, also in terms of variables like we did in those ones. Ladies and gentlemen, just in 1 minute quickly. One of the colleagues asked me about 180, 360 and tan. What I did in the grade 11 textbook, not in the grade 12, it is in the grade 11 textbook. I pretty much like when I do equations and I have an equation with tan, then what I like to do is to do it exactly the same as what I do with sine and cos. So the general solutions, I don't write it as 180. But if you write it as 180, you will agree you only need one solution. That's why I said when the other person asked me that question earlier. So for tan of 180, one solution will give you all. So you're 100% welcome to use it. I love to use 360 because then my method is the same. So my method for sine, cos, and tan are the same. I use all of them 360, so you will get 2 solutions. You will get one because you are using not 180, you now need to write down the solutions for both quadrants, where you only need to write down the one solution if you use 180. I hope that makes sense. If you look in the grade 11 textbook, I say it there explicitly. I give the 2, and then at the bottom in the example, I say it can also be written as one solution, and then you write it as one solution. Okay, ladies and gentlemen,